wonder if I can get it to be.
Function.
No.
That one there.
Okay. Can I get
Try function and that.
function and that one? Okay, just a sec. Let me see if I can get mirroring working. That will ease my.
Just by way of introduction, Keijo is an associate professor at Aalto University in Finland, and he's been working on the Hadoop-BAM format we mentioned earlier, as well as other frameworks like Seqpig. I think you're going to talk about today.
Yeah. Okay, that's not looking too good. Let's see, my machine doesn't like. Okay, let's see. Let me retry. Let's try. Yeah, that's the other option. Let's see if we can get displays. Maybe I'll just open recent. That should be it. Okay, I'll manage this way. Okay. Hello, everybody. So my name is Keijo Heljanko. I'm an associate professor at Aalto University. I work with Hadoop-related things for 4 years now. So I'm going to talk about a project called Hadoop-BAM and Seqpig. And these are basically Hadoop-BAM is basically a library to interface, I would say, legacy file formats to Hadoop. And these are the collaborators, so all the real work has been done by Andre Schumacher and Matti Niemenmaa. Andre is an ex-postdoc of mine, Matti is an ex-master student of mine, and then the current maintainer is Ridvan Döngelci. And also we've gotten source code contributions from Luca Pireddu from CRS4, and then other collaborators include people from CSC, which is the Finnish Supercomputing Center that has a bioinformatics group. So Aleksi Kallio and Eija Korpelainen over there. So next generation sequencing. So what is it all about? So the amount of NGS data is growing as we've seen in the previous talks. And this growth has been estimated to grow double every 5 months. And this is much quicker than Moore's law, which is doubling of compute power every 18 to 24 months. It's also faster than Kreider's law for the growth of storage capacity. So storage capacity is doubling every roughly year. And also quicker than Butter's law, which is the network capacity growth, which is doubling every 9 months. So without increased expenditure in compute, storage, and networking capacity, you're not able to maintain the data growth volumes that you have on the bioinformatics side. And there's also other bad news. So if you haven't been following computing, Moore's law is also kind of breaking up to a point. So around 2005, there was a paper by Herb Sutter, The Free Lunch is Over, which basically said we're not going to get faster computers anymore. So in 2005, the growth of a sequential throughput of a computer stopped improving. We're still getting more transistors for a while. So Moore's law, in parallel, if we parallelize software, is still going to help us a bit. But if we just work with sequential codes, like many traditional bioinformatics pipelines are, then the kind of discrepancy between things is going to be even harder. Okay, let me see if I can get this working. No. Okay, so we're not getting faster computers, but we're getting more transistors. And because of this, if you want to get at least the benefit of the increased number of transistors you have in increased number of cores, you have to go parallel. So you have to start using parallel programming frameworks to be able to utilize all the transistors that are available. And the programming models need to change because basically we're entering the era of parallel. You always need to program in parallel. And the scalability to high number of cores is going to be a new focus here. Okay, let me see if I can manage on this side. Nope. Okay, well, just a sec. Do I have? Okay. Gather windows. And let me see. Arrangement. Mirror displays. Oh, now I have it here as well. Okay, another thing that I quite often talk about to my students is the cost of different storage formats. Here's a trend of historical trend of cost of storage. So what's the cost of storage for hard drives? What's the cost of storage for main memory, and what's the cost of storage for flash storage? And what you see here is the gap between hard disk storage and main memory is like 10 years in time. So if you 10 years ago were able to store some data set in hard drive, today you should be able to store the same data set in main memory using the same amount of dollars or euros. So for those data sets that you had 10 years ago, you should process them in memory because memory is much faster than hard drives. So RAM and SSDs are radically faster than HDDs. So one should use RAM and SSDs whenever possible. Workloads that were viable a decade ago on hard drives are viable now in main memory. So we have servers in our cluster that have a terabyte of main memory. And you can do very interesting data processing tasks there very quickly. And one should only use hard disk-based storage for data sets that are not yet economically feasible in main memory. So there's lots of small data that can fit into the main memories of all the servers you have in your computing cluster. And for those, you should use a computing framework that uses main memory efficiently. And there are things like in-memory distributed file systems, Tachyon from the Spark guys in Berkeley, being one of the examples which can help you with things like storing the temporary files that are in these pipelines. So many of the pipelines have a lot of temporary files that need to go from one set of processing binaries to another set. So the amount of I/O you need for that might not have to go all the way to the hard drives. It might stay in memory if you have the correct infrastructure for that. So the big data applications should consist of those which are new data, which you just couldn't store 10 years ago because of cost reasons. So what's Hadoop? Jim talked about this a lot. So Hadoop, I see it as an open source distributed operating system distribution for big data. So it's not anymore like the MapReduce programming framework. It's starting to be more like a Linux distribution that companies like Cloudera and Hortonworks are running in the same kind of mode as Red Hat and SUSE have been running, just integrating a lot of open source projects into a single package and testing it together. It's initially based on Google architecture design. It's using cheap commodity hardware that Jim talked about. There's distributed file systems, HDFS for hard drives, Tachyon for main memory usage. There's batch processing, MapReduce. Hive and Pig are hard disk-based frameworks. Spark is mainly RAM-based, but also can do hard disk-based things. There's parallel SQL implementations. So there's frameworks like Hive, Impala, Shark, Spark SQL, and Presto that are able to process petabytes of data in a single database system. We have fault-tolerant distributed database like HBase that you can use for indexing data. We have machine learning, etc. And as said, MapReduce is just one application on top of the Hadoop stack. So it's like, if you ask duck cutting what are they doing, duck cutting being the main inventor of Hadoop, he says, well, we're building a distributed operating system. He's not saying that, okay, we're building a programming framework called MapReduce. Okay, so here's a couple of companies, Cloudera, Hortonworks, Mapper. Just to get an idea, Cloudera got $740 million US investment from Intel for 18% of their shares. So they now have quite significant funds available to invest on the software framework. And there's also other players like Databricks commercializing the Spark support. Okay, so back to what have we been doing. So we've been doing a framework called Hadoop-BAM, and it's a library to interface NGS data formats with both Hadoop and Spark. Why Spark? Because Spark is able to also use the same Hadoop input formats as we originally designed this tool for. It includes some tools. For example, there's a very fast parallel sorter. So if you do, for example, read alignment in parallel and you get like 50 files, you can sort them together using one of the binaries in the Hadoop-BAM distribution to a single sorted file format. The supported file formats are BAM, SAM, FASTQ, FASTA, QSEC, BCF, VCF. We've accepted before already contributions from Italy to add more file formats, and we're happy for any outside contributions to this. So it's been released 4+ years ago. We're currently at version 7.0. We have like 2,800 downloads of the library. There's the bioinformatics paper that is the kind of the main thing to cite if you need to cite this at some point. And from that paper, we have some results on the scalability of some of the experiments. These are now already old experiments, and these are kind of sorting in parallel. This is sorting with 15 machines in parallel. This is the optimal speed up. We're not quite there, but we're doing pretty good. But one of the things we learned at that point was that if we use a standard off-the-shelf storage framework, like we were using a Lustre storage system to upload the data to Hadoop, that storage system became the bottleneck for the data. So just importing and exporting the data to the Hadoop-BAM and the HDFS took most of the time. So basically you wouldn't get any speed up if you just relied on traditional storage systems. So if you want to get good performance, you either have to move to a very high-end storage system or build it out of HDFS to start with. That was the main thing in these experiments. Okay, so Hadoop-BAM, what should I say? As said in here, some file formats like BAM are notoriously badly designed. And I can say it on the record. And if anybody's designing file formats, please come talk to me. Why is it badly designed? Well, first of all, it's a compressed file format, and we have to process it in parallel. But there's no index in the compressed file format. So we have to, for example, if we want to read some data at, let's say, at offset of 2 gigabytes, we have to go at 2 gigabytes and figure out, okay, when does the compressed ZZip block start? By looking for a magic number. So we look for a magic number. Then we, once we find that, then we uncompress some data, check if the CRC32 checksums check out, and then check whether the next block checks out also okay with the CRC32 checksums, etc. So that's one of the nasty things. But not only that, then there's also no index inside the uncompressed data. So you will land up in the middle of the data stream and you have no idea what is the data inside there. And then you have to figure out by the redundancy in the file format, okay, am I in the middle of a record or am I off by 1 byte? And then we do things like we parse 10,000 records to get the right offset to figure out, okay, oh, now we have the right data. Or we can do 2 paths, you can choose. The default is to do these trickeries. So basically, it's a horrible file format for parallel processing. Hadoop-BAM has all the nasty kludges needed to make it work. And many of the tools seem to be using this as an I/O library, and we're happy to do that. So we see ourselves as a kind of a bunch of people who are maintaining an I/O library to read these nasty-to-read file formats. Okay, Seqpig. Well, Seqpig was another project that we started. This is a parallel scripting language for NGS datasets. It's based on the Apache Pig language, which is a language that has SQL-like functionality. So this can do database queries. It compiles into Java. It's executed by Hadoop MapReduce. It can do filtering, computing aggregate statistics, doing joins. These are the file formats supported currently. There's a bioinformatics paper on that. There are some examples in the supplement. Here are some example use cases. So we can automatically parallelize Pig scripts for file format conversion. If you need to do, let's say, BAM to SAM conversion or from BAM to some native Hadoop format conversion, then you can do these in Peg. You can do filtering. You can do sorting. You can filter by regions. You can compute read coverages, base frequencies. You can even do pileups, though it's not too good in doing pileups. You can collect read mapping quality statistics per base statistics of reads. Simple things that people usually write Perl scripts for. But this actually auto-parallelizes, and this is what we get. So this is things that are run actually in the Italian cluster. So we scale, for some scripts, we scale up to 50 computers running in parallel, each one having 12 cores. So this is now then several hundred threads running in parallel. And these are scripts that are usually 5 to 10 lines of code. So the programmer doesn't have to know anything about the parallelization. He or she writes the small scripts that kind of describe the steps needed, and then the framework does the rest. And this is a very nice framework. So what are the benefits? Well, it's auto-parallelization. For scripts, like quality control might be a very simple thing that people use this for. Most scripts are tens of lines of code versus hundreds or thousands of lines if you would write the Java program to do the same thing. It allows calling back user-defined functions. We've written some example functions for different NGS filtering tasks. And you can go and check our paper and the supplement for some example scripts. What are the drawbacks? Well, it's based on MapReduce, so MapReduce has a 10+ second startup delay, so it's not really for interactive use. And it's a specialized language, so you have to learn this specialized language if you want to use it, unlike just using a standard database, standard language like SQL. So then let me talk about some recent improvements. So we'll hear more about Spark later today. Spark is a fast general purpose, mainly in-memory cluster computing system. It can cache data sets. It's more suitable than Hadoop for iterative algorithms, and it has a way faster startup delay than MapReduce. It can be up to 100 times faster than Hadoop. It runs standalone in Yarn, Mesos, and EC2. And it can use HDFS, HBase, and other Hadoop sources, including Hadoop-BAM. So this is nice. Now there's a project called Spark, which is Pig on Spark, which can run existing Pig scripts with minimal changes. It compiles into Spark jobs instead of Hadoop jobs and can extend the cache operator. It's open source. It's still alpha, so buyer beware. The code base is out there, and you can take a look at the issues. And the basic idea is the following. So we have our Pig scripts. For example, you can take our example Seqpig scripts. And instead of going through the MapReduce execution plan in Spark and in Seqpig, that's our new version of Seqpig, we generate Spark jobs out of the thing. And Seqpig can run existing Seqpig scripts. It compiles into Spark jobs instead of MapReduce jobs. The speedups we see are not great. There are two is typical, 4 is something we see, but not more. The code base is out there in Ridvan's GitHub. It's not released yet, so we'll probably write a paper on this and then make more noise about this. So this is very, very early. The advantages is it's more flexible and faster. There's caching functionality, so you don't have to write all the data between stages of your scripts to temporary files like you have to do in Pig, in standard Pig. Data processing is done mostly in memory. So for many of the things which do not need the hard disk processing, you can actually get way faster processing speed. These advantages, the Spark project is very early still. So it's still alpha quality software. It's somewhat unstable. It's not declarative like SQL, and there's still startup delay. So this is what Ridvan is currently working on. So we're increasing the stability of the framework. We'll address some of the performance issues in group and join operations. So these are kind of, the Spark group has mostly focused on functionality and not performance tuning yet. So we probably have to contribute some things upstream to get better performance on these things. Implement more genomic functionality. And we're interested also in parallel variant calling. Right, and then the last thing I want to talk about is moving BAM files to SQL data warehouses. So a proper data warehouse system, what can it do? What, let's say, traditional frameworks cannot do. It can, for example, very efficiently evaluate parallel queries over petabytes of data in parallel. It can allow for efficient compression and indexing, including indexing several BAM files into a single table. So you can import all your reads into a single table, and then they do queries on them. And there are many now new analytic SQL implementations on top of Hadoop designed to handle petabyte scale queries. Hive, Impala, Spark SQL, and Presto are the most widely known systems. And the good thing about these is most of these actually are compatible. So you can import data through Hive and then query the same data tables through Impala, Spark SQL, or Presto. or vice versa. So they can actually work on the same database tables, which is very nice. So what do we have? Well, we actually integrated Hadoop-BAM to Hive. So Hive can now directly read BAM files. And it can actually convert the NGS files into columnar storage formats. There's a lot of work being done on big data side for efficient file formats for data. And columnar storage formats like RC file that we've mostly been using, and Parquet that we've also tried out, are much improving in getting queries. So using RC files or Parquet also allows these things to be queried by Spark SQL and Shark, it's an earlier version, Impala and Presto. So we have a thesis, this is by the main author of Hadoop-BAM. He finished his thesis in December 2013. It's out there on the web. You can Google up the thesis. That has all the details of the experiments I'm going to show you. And the interfacing goat is out there on the net, but we haven't done a proper release of that one yet. So it's available on request. So here are some benchmarks that I'll show as the last thing before my conclusions. So these are now already a year old. So basically what we did, we used Hive to import data from BAM to an RC file, which is a columnar database format, in order to for all the reads to be accessible by all the different parallel SQL query engines, and then benchmark different SQL queries on the BAM files. At the point of time, the frameworks were Hive 0.11, Shark 0.7, Impala 1.01. Now I have another student who's redoing the benchmarks with newer stuff, including Spark SQL and Presto. So maybe in a month or two we'll have some newer numbers. Hive was very stable in these benchmarks, but it's never faster than 10 seconds, making it unsuitable for interactive use. So of course you would love to have all your BAM files and get your queries down to, let's say, sub-second query times for some of the queries you do. The other frameworks, Shark and Impala, did really well on small queries. On large data sets and node counts, so the number of computers grows. Hive catches up with the other systems. And at the point we were testing, both Shark and Impala had stability and or correctness issues. So here's some benchmark results. So this is kind of a scatter plot of different SQL queries. We had a bunch and we ran them. And we were running with 1 computer, 2 computers, 4 computers, 8 computers, 16, and 31. So these are SQL queries being queried in parallel with using 31 computers. The green ones are Hive. So the Hive is the slowest on small node counts. Then we have Shark and then Impala being fastest on small node counts. But there's interesting effects, like at 4 workers, suddenly Impala performance blows up and is very bad. So it gets slower by adding more machines. So there's some bug in there, obviously. If we then zoom in by using log scale instead of linear scale, so now we can see, for example, that Hive never completes any hello world query even below 10 seconds. So if you ask it anything, it will take 10 seconds, no matter what. The other frameworks, they can get to sub 1 second query times for the smallest queries. And I'm really curious to see what this looks like once we take a look at the latest versions of the parallel SQL query engines. So future plans. So this is basically the end of my talk. So what are we doing? We're porting all our stuff over to Spark from Hadoop. We have some collaboration going on parallel variant calling using black box variant callers. So we see the same thing as Ulf sees, that everybody likes to have their own variant color, and you somehow have to just cope with it. It's work in progress. We're not too far, so if anybody wants to help us, all help is appreciated. We would love to have Seqpig-like functionality with Hive. We have kind of I would say alpha code to interface BAM files to Hive, but we would love to do collaborate with somebody who really cares about getting SQL running for more than a single BAM file, like maybe 100 BAM files. I think it's wise to move to columnar data formats. Parquet and RC file are the one we work with. Basically because then you can just use standard Hadoop tools. You don't have to do anything NGS specifics. Of course, then you have to have nice import and export functionalities. We have import functionality, we're still lacking export functionality here. We have it through Seqpig, but that's a bit clumsy. We don't have it in the framework itself. Interactive ad hoc queries, we want to get sub 1 second query times for many things. In-memory file systems, I think they are really needed to get the pipelines fast enough. If you just keep on pushing all the data to a temp file and then reading it back 10 times over, it's not a good use of I/O bandwidth. HBase would be nice to integrate. And I'm here, so please come to talk to me. We're happy to collaborate with anybody and everybody. And if anybody has patches for Hadoop-BAM, we're more than happy to put it in, or new file formats or anything. So thanks, that's it. Any questions?
So what are the type of SQL queries you are running? What is the data model? What is
So
what are you querying and what are the types of queries?
So you can go to the thesis to find the exact queries, but they're like join with a bed file, throwing most of the data away. They are things like performing all kinds of quality control aggregates.
SQL query.
Yeah.
Okay.
So
I need this.
So it's on the web. I think I can either send it to you, or you should be able to Google it up using the title of the thesis. Yeah. What?
I was wondering about the big graph that you showed.
Yeah.
The GC calculation is the thing that throws back the performance, the
Yeah.
bottleneck. Do you know why is that?
We didn't do a very thorough, let's say, we didn't do a very thorough analysis of this. The gut feeling we had was that maybe the data volumes are not big enough. So the startup overheads of MapReduce are gonna eat into any speed ups you might have. So this is what was our main theory. But
Compare that to the second code,
I don't. So I don't have those numbers yet. My student has those, and I haven't taken a look at the detailed numbers yet. Yeah.
Yeah, just one question
Yeah.
again on the SQL and what Phil mentioned. Have you looked at the Google Genomics SQL API and how that?
That's on my to-do list of things to read. So definitely I want to have that. So we have SQL plus a couple of UDFs, but yeah, okay.
You have. I was googling that you have 2 pages. One is in a source force, another one a GitHub.
Yeah.
Which is more fresh?
They're supposed to be in sync. I would say, so we do the official releases in SourceForge still. Why? Because we get nice download statistics, but yeah, all the real code development is done in SourceForge. So, sorry, GitHub. So SourceForge for kind of official releases, GitHub for things that are not maybe ready yet. Yeah.
So you talk about BAM a lot. For VCF files or the GVCF format, which has, there's some notion of calls, reference calls, where you don't call different reference.
Yeah.
So I would like, I mean, I know the data is sort of much smaller than BAM.
Yeah.
It's a point estimate, the VCF files. But still, I don't know whether there exists, say, a VCF data store where I could do SQL analytics against like 100,000 VCFs. Have you looked at that at all?
We've been so far concentrating on BAM, but if anybody has enough VCF to care, we'd be happy to take a look. So I have a lot of hammers, but I don't have enough data sets. Okay. Yeah. Cool.
Actually, why is Spark only 2 times faster?
That is a question I asked my student, and we don't have an answer yet.
Matter of Spark, or is it
I think there's something going on with Spark not being optimal. So I think doing this in native Spark might be faster. This is my gut feeling.
I mean, if you move to Spark, it should be much faster.
Yeah, but this is okay. We've also used Spark in some other frameworks. It's like okay, this is now hearsay. Okay, maybe there's these Spark guys that gonna counter me in a sec, telling you the true story. But it's like the smaller the data set, the larger the difference. So we have some SQL queries where Hive is catching up Spark once we grow the data set big enough.
What I would say there is that Spark's performance benefits the more the deeper your pipeline grows. So if you have a job that's highly iterative, then Spark will greatly outperform Hadoop. On a single stage query, so Spark used to be slower than Hadoop for a single stage. Right now they're at, depending on what exactly the job is, between parity to sometimes Spark being faster. So if you have a pipeline that's not very deep, then you're not going to see a huge difference between Spark and Hadoop.
Yeah, this is definitely not deep. This is single stage things.
Exactly.
So maybe that's the correct explanation for it.
Yeah, well, and it's for some things Spark does have very efficient internals. So a lot of Spark's been really working on the shuffle code. So stuff that's shuffle dependent is starting to be very good in Spark versus Hadoop.
Yeah,
for a single stage, it's
we see newer versions of Spark being more and more competitive for big data sets. So yeah. But the bottom line is we're using both, but we're kind of moving all our stuff to Spark. So we're believing that's where it's gonna go. But for some production things, you might still run Hadoop. Okay. Thanks.
Okay, we have lunch now, and it's like I mentioned earlier on,